Ladies and gentlemen, we are going to start today with chapter 4, and we are making use of the textbook of Cengel and Ghajar, the 5th edition. And before we start with chapter 4, which is on transient heat conduction, I just want to do a little bit of a revision of the previous 3 chapters in the textbook, which is about a general first chapter on the 3 different modes of heat transfer, and then the chapters after that, which all concentrates on steady state heat transfer. So the very important work is steady state there. And let's just revise quickly the 3 different modes of heat transfer. The 3 different modes are firstly, conduction heat transfer, and conduction heat transfer is the equation for that is equal to minus k multiplied by the area dt dx, temperature gradient. However, later on in the last chapter, actually chapter 3, what you did is you wrote it in this format of a temperature difference of 2 surfaces divided by a conduction resistance. And this conduction resistance, there can be different possibilities. For example, the plane wall, which is the simplest case, which you have started with, and that might be the plane wall like that, with surface area AS, and that is the thickness of the plane wall L, and the surface on this side is equal to T infinite 1, and the temperature on that side is equal to T infinite 2. So there's a temperature difference over the plane wall, and for that case, if you just go and work through the equations, you'll be able to derive the so-called resistance for the plane wall, which is equal to the thickness of the plane wall divided by the thermal conductivity multiplied by the surface area through which the heat transfer occurs. So the heat transfer, if I can use a red color here, is actually then in that direction, the heat transfer rate from the one surface to the other surface, the case of a plane wall. Then there were more complicated cases that you also derived and looked at. For example, a cylinder, where you've looked at something like that. And this cylinder will have a length L in that direction. Take note, L here is not the thickness. The thickness is being described in terms of R1 and an R2. So this is for a cylindrical case. So that's cylindrical. And again, there's a surface area AS, which will be the outer diameter multiplied by the length. And for that case, and again, there will be a temperature T infinite 1 there, and a temperature on that side of T infinite 2. And then for this case, the resistance of a cylinder can be written as the ln of R2 divided by R1 divided by 2 pi Lk. I hope you remember that. Well, you don't have to remember it. It is in your textbook. You must just know where it is. And then there are other cases also. There's a case for the sphere and other types of geometries of which the resistance term has all been given. However, if we look at the conduction heat transfer, what is important is the conduction heat transfer rate is equal to a temperature difference divided by the resistance. and the resistance will depend from geometry to geometry. And the resistance will always have in it the thermal conductivity of the material and the geometry characteristics like the length and the radius, etc. Right, so that is conduction heat transfer. Then the next one is convection. For convection heat transfer, the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied temperature of a wall minus the temperature of the environment. So if we have one at a surface here, and I'm going to show you two different scenarios where that temperature is equal to T of the wall and the temperature of the wall. Here, you're going to have a velocity that flows over this plate, which is at a different temperature than that of the air or the free stream. I'm showing this arrow because it has a little bit of length. It has a little bit of oomph. Okay? So it can be 10 meters per second, 100 meters per second, 1, 0.1, 0.05, and somewhere you get to a point where this velocity is really so small that it has the same effect as smoke. It goes up because of the density differences. So the velocities are very, very small. So this is called natural convection, and that is called forced convection. Forced convection conditions are normally you have a pump that would pump a liquid over a surface. You've got a fan that would force it over, or it's a windy day and you've got a surface on the outside and there's heat transfer from the surface to the windy day. But very important, there's quite a significant velocity. What significant is, that is debatable. In the case of natural convection, there's always gravity. Okay. The changes in the velocity is being caused by changes in density, which then means that if you're out of the atmosphere of the Earth, far away from here, then G is equal to 0, and then there is no natural convection. It cannot occur. The heat transfer can only occur via forced convection or then radiation. And the radiation is the next one that we're going to get to. So for convection heat transfer, we can write again that the heat transfer rate is equal to a temperature difference divided by the resistance of convection heat transfer, and the convection resistance is equal to 1 divided by the heat transfer coefficient multiplied by the surface area over which the heat transfer occurs. Do you remember that?
For the forced convection, we neglect gravity.
For forced convection, no, we do not neglect gravity. Normally, the inertia effects will be much larger than that of the viscous effects. So gravity is still there, but it wouldn't play a role. Any other questions? Right. Now the third mode of heat transfer is a little bit more difficult, and that is the radiation heat transfer. Radiation heat transfer, and the radiation heat transfer rate is equal to the emissivity multiplied by the Stefan-Boltzmann constant, the area over which the heat transfer occurs, multiplied by the temperature of the surface to the fourth minus the temperature of the surroundings to the fourth. Where the emissivity of 1 would be an ideal black body. I don't know if you can remember from physics, people did the experiments where they've got a spherical type of object with a small hole through it. The radiation would come in, it would reflect around, etc. So that is by definition a black body. It is a surface that can actually absorb all the radiation heat transfer. Just to give you an idea of different values of emissivity, 0.07 if you use an aluminium foil. Okay. Aluminium foil, when you use a value of 0.07. White paint is 0.9. So you shouldn't think of the color. That has an influence on the emissivity. And then for water, it is 0.96. So water absorbs a lot of radiation. So that is why if you're swimming just underneath the surface of the water in a swimming pool, you're still going to get sunburn. And then lastly, about 0.95, that is the human skin. So the human skin absorbs a lot of radiation. And typical values, if you're interested in more values, in table 1.6 in your textbook, there are some more details that you can get. It's not a long list, but in the appendices of the textbook, there are many more that you can go and look at. Okay, now in many cases, these heat transfers do not occur on their own. In many cases, we've got a combination of the heat transfers. For example, let's look at the case where, and I think you've all experienced that. We are going to look at a room, okay, and you're going to stand in the room without your clothes on, and now this is the thermostat of your air conditioner. So you've got a very fancy air conditioning unit in your room or in your house, and this thing shows there, like that, shows the temperature, and that temperature can be, so that's the temperature of the ambient, is 22 degrees Celsius. And your temperature, what would your temperature be? Your temperature would not be 37, that would be the temperature inside your body, but the skin temperature will be about 30 degrees Celsius. And because of this air conditioner, the heat transfer coefficient is going to be 10 watts per square meter degree Celsius. And your surface area is 1.4 square meters. And what you're going to experience in winter, you're going to stand in this room where the temperature is 22 degrees Celsius. You should be comfortable, but you'll feel chilly and cold. Okay? While in summer, you're not going to experience that problem. Temperature of the air around you is exactly the same. However, there is one difference, and that is that the average temperature of your surroundings, that is now the temperature of the walls, your bed, and everything that is in your room, all around you. So that surroundings temperature can be 25 degrees in summer or 10 degrees in winter. Those are the two different scenarios. And we are going to look at these two scenarios, trying to explain why you have the feeling of it is chilly, although you are surrounded by the air, which is at 20 degrees Celsius in winter, while in summer you feel comfortable. So the mode of heat transfer that we have here is that of two modes of heat transfer. And take note, I'm going to write these two resistance terms. I'm going to show them schematically that they are different. Later on, we will see if they are different and which one of the two is bigger than the other one. That is very important for paragraph 4.1 in the textbook of chapter 4 that we are going to look at when we get to the Biot number. I will introduce that to you a little bit later. Okay. So this is U, that is the temperature of, we set Ts, that is your surface temperature, and that is going to be the convection resistance, and that is going to be the radiation resistance. So the convection resistance is going to work to the ambient air, because that is what is around you, and it is being moved by the air conditioner, and for that the heat transfer coefficient has been given as 10 watts per square meter degree Celsius. So that is the convection, and then we've got the radiation. Now the radiation temperature is not being influenced by the air temperature. It is being influenced by the temperature of your surroundings. This would now be the total heat transfer rate through there, and that would be the heat transfer rate of convection, and that would be the heat transfer rate of the radiation. So let's go and do the calculations and see what happens. Oh, wait, let's first do the convection heat transfer. The convection heat transfer is equal to the heat transfer coefficients multiplied by the area multiplied by the temperature difference is Ts minus T infinite. Okay. Take note, we can use the temperature difference in degrees Celsius or in Kelvin. It's not going to matter because it's just the difference between the two. The heat transfer coefficient is going to be 10, that has been given. Your surface is 1.4 square meters. Your surface temperature is 30, and the room temperature is 22, that of the ambient. So if we calculate that, then it is equal to 112 watt of heat transfer to the surface air. However, let's look at the radiation heat transfer in winter. In winter, it's going to be the asymmetry multiplied by the Stefan Boltzmann constant multiplied by the surface temperature minus the temperature of the surface to the fourth minus the temperature of the surroundings in winter to the fourth. So the emissivity of the human skin is 0.95. I've already showed that to you. Multiplied by the Stefan Boltzmann constant, 5.67, multiplied 10 to the minus 8. Multiplied by the surface area, which is 1.4, multiplied by the temperature difference. However, take note, because of this, we have to work in Kelvin. We cannot use it in degrees Celsius. So the surface temperature is equal to 30 plus 273, everything to the fourth, minus 10 plus 273 to the fourth, like that. And the result is that the radiation heat transfer in winter is equal to 152 watts. Okay? Any questions? Also now in summer, calculation, again, the emissivity, Stefan Boltzmann constant, the surface area, the temperature to the fourth minus the temperature of the surroundings to the fourth. And now it's going to be in summer. So the only term that is now different is this term. You see, in winter it is at 10 degrees, and in summer it is at 25. So you need to write down all those temperatures, and now we're going to have 25 plus 273 to the fourth as the last term. Quite sure I do not have to write it out for you, all of it. It's very simple. And now you can go and calculation the heat transfer rate of the radiation heat transfer rate in summer is 40.9 watts. Let's look at the total for the winter. Is then the radiation heat transfer in winter plus the convection heat transfer. Okay. The radiation heat transfer is equal to 152, and the convection heat transfer is 112, and that is equal to 264 watts. And in summer, it is 40.9 and 112, and that is equal to 153 watts. Do you follow that? Take note of the radiation heat transfer. And so in terms of the radiation heat transfer, the heat transfer rate is about 3 times lower from winter to summer, but the convection heat transfer rate stays the same. If you would be in your room and you would go out at night where nobody can see you and you stand outside, what is then going to happen? Your surroundings temperature, that winter temperature, is going to drop. It's going to be lower than 10 degrees Celsius. In the last chapter, the last 2 chapters, you're going to do a radiation heat transfer, and then we're going to get to a temperature which is called T-sky, which is the average temperature of the black sky around you, and it will be different from nighttime to daytime. But those details will follow later. Right. Any questions, ladies and gentlemen? Right. All the problems up to now, we had a body. And what was important is that the temperature of the body remained the same. So the temperature was not a function of time, because it was constant. All the temperatures, the temperature of the environment, the body, etc. We did not take into consideration any possible changes in the temperature. A possible change in the temperature might be you changing this temperature. You maybe do not want 22, you want 15, or you would like to increase it to 30. Then the temperatures is going to change as a function of time. And that is what chapter 4 is all about. Chapter 4 in your textbook is transient heat conduction. transient heat conduction. So transient heat conduction, or transient, would imply changes. Goodness. So transient. So again, if we now look at this graph of temperature as a function of time, then where previously we had the temperature which remained constant at a certain t equals 0 or whatever, t equals 10 seconds, things are going to change. And it can be either the temperature of the environment or it can be the initial temperature of a body. So one of the two is going to change. And then we are interested to see how the temperature difference will be in the body as function of time. And take note, it is transient heat conduction. So it has to do with the heat transfer inside a body, like for example, a plane wall or another type of geometry like that of a cylinder and a sphere. I'm just going to clean the board here and continue here because it seems as if we're getting feedback on the microphone or on the sound system when I move too much to the right. Okay, and that brings us to paragraph 4.1, which is called the lumped system analysis. Lumped system analysis. And for the lumped system analysis, we're going to have any type of body, an arbitrary body. It's going to be a solid material, and this solid material is going to have a certain m, which is mass. It's going to have a certain volume. Take note, my V is a little bit different. And in the textbook, there's also a V which looks a little bit different than the normal V, which is velocity. So that's the difference between the two. So this one is volume, and then there is density, and then there is an initial temperature inside the body. And the body is at a uniform temperature. There are no temperature differences. And on the outside of this surface, we have the surface area. We have a heat transfer coefficient on the outside, and we've got T infinite, which is the temperature of its environment. And in this case, we are not going to take radiation into consideration. Okay. So we're only going to look at convection and conduction. So convection and conduction only in this work. Right. Now, what you will see is that in many cases where we get to a temperature difference, in some cases I'm going to write it as T wall minus T infinite, and in other cases I'm going to write T infinite minus T wall. And usually I will put the largest one there because it's so simple and intuitive that we know what the direction of heat transfer is. It is always from the highest temperature to the lowest temperature. So in a problem like this, it might be that this environment is at a higher temperature than that, which means the heat transfer rate would be from there to there. In some problems, it might be that this temperature is lower than that, which then would mean the heat transfer rate is just in the opposite direction. So in general, except for one exception here when we are going to do a derivation, the sign is not important. It is not as important as in thermodynamics. So, in terms of solving this type of problem, what we're going to say is that the heat transfer into the body over a certain period dt, change in time, is going to be is equal to the increase in the energy of the body over a period of dt. What does it mean? It means that if we put in 100 watts and we measure for 1 second, then it means that 100 joules has been transferred to the body. If that happens, the body receives that heat, isn't it, over the period of 1 second. Now you can do it for 1 second or 1 hour or whatever, it doesn't matter. What goes in stays on the inside. Okay. So in terms of writing this now mathematically, we are going to say the heat transfer inside the body is convection heat transfer. So it is equal to the heat transfer coefficient multiplied by the surface area multiplied by T infinite minus T of the temperature of the body. Remember, this is not Ti or T infinite, it is T as a function of time at any period of time. The heat transfer coefficient multiplied by the surface multiplied by the temperature difference is equal to m Cp dt from your thermodynamics divided by dt. Does that make sense to you? Okay. So this we're going to write as T infinite minus the temperature as a function of time divided by dt. So I'm just putting all the temperatures on the left. There's a term dt, which is also the temperature, is then equal to the mass multiplied by Cp divided by the heat transfer coefficient, the surface area over a period of dt. You see that? Then we're going to say, well, the mass is equal to the density multiplied by the volume. You can keep it the mass if you want to. You do not have to write it like that. And the temperature, on the left we're going to write it as T infinite minus the temperature T, d T minus T infinite. Remember, the variable is that value there of T, as well as that value of T there. So if I differentiate by putting in a constant, you've done it many times in mathematics, is then equal to rho multiplied by the volume Cp divided by the heat transfer coefficient, surface area multiplied by dt. Now, what you now can do is you can take the dt's and multiply it by the minus just to get rid of it. And the result is that you're going to write this equation as dt minus t infinite divided by t minus t infinite is equal to minus the transfer coefficient, the surface area, rho volume Cp, and the dt. And you can go and integrate it from 0 to t, the time t, and the temperature is going to be the initial temperature up to T environment.
Why is it that it was T infinity minus T?
You just need to, if you change this, then you multiply it by -1, then you just take it through to the other side. So I've skipped a few things here, just go and check it, it is correct. And this is the same as having the integral of 1 divided by x. The solution is the ln of it, and then you get rid of the ln by writing it in the following format. The temperature minus T environment is equal to Ti minus T infinite is equal to e to the minus bt, where b is all a constant, and that is equal to the heat transfer coefficient multiplied by the surface area divided by rho Vp, divided by rho the volume and Cp. So the possible solutions of that equation is always one of the two. And between the initial temperature and the environment temperature. Let's suppose the environment temperature is larger than in the initial temperature. Then the temperature as a function of time, the solution is going to do something like that. After a long enough time, the temperature of the body is going to be the same as that of the environment. You agree? Okay. Now, depending on the value of B, there might be different solutions like that. So if B increases, then it will reach the initial temperature quicker. That is the one possible scenario. And the other scenario would be where that is the initial temperature and that is the temperature of the environment, and the initial temperature is higher than that of the environment, and the solution is going to do something like this. Do you agree with that? And in terms of temperature, okay, we can actually do it like this. That's temperature as a function of time. That can be T equals 0. It's an arbitrary definition of when do you want to define it. But before T equal to 0, the temperature in the body would be a steady state. With steady state conduction, the work that we've done in chapters 1 to 3 is irrelevant. But the moment the things change, the temperature of the environment, we are going to have something like that. And this is called the transient solution. And this equation would describe this transient solution, equation 1. Okay. Now, except for the fact now that we've looked at this body, okay, in terms of the environment, let's just go back to the beginning of the lecture where I did some revision. If we have a body like this, and here is the temperature of the environment, and we do not take into consideration radiation heat transfer, then it means that that temperature there is maybe the initial temperature, and then there will be the resistance of the body, and then there will be the resistance of the convection. So the two terms that you have to look at is the conduction resistance and the convection resistance. So the heat transfer rate would then be equal to the heat transfer of the conduction plus the heat let's write it down. Okay, wait, yes we can. Okay, so the heat transfer rate would be equal to Ti minus T infinite divided by the total resistance. And the total resistance is then going to be influenced by the resistance of the conduction plus the resistance of the convection. And there are different possible scenarios. Let's look at a few of them. So that is Ti, and that is T infinite. And the one scenario is that we've got two resistance terms, which the order of magnitude is about the same. And with order of magnitude, if it's 10 or 20 or 90, order of magnitude the same. It is just not 10 and 100. Magnitudes of 100, 200, 300, etc. So we've got two resistance terms there. But then we can have some other extremes. And that is the extreme where that resistance, so that of conduction, the resistance of conduction, and then we've got that resistance term there and there. That is where that conduction resistance is almost zero, close to zero. And this one is going to be a value, maybe 100 or something like that. But in comparison with 100, this value is maybe going to be 0.001 or something like that. So that resistance is extremely small. Then we can have the other extreme, and that is this resistance is all the resistance of conduction heat transfer. While when we get to the convection heat transfer, it's almost zero. So the convection heat transfer is almost zero, and the conduction resistance would exist. Right. So the resistance is like the opening of that door. Okay. If I would ask all of you, or let's suppose there's an emergency, and all of us have to get out of here, and everybody wants to go through that door at the same time, then the resistance is small. Do you agree? It will not be possible to get everybody through that door in 3 seconds. Okay. However, if we make the resistance very large, so knock down all the walls, there's nothing, and we are in an open field and we have to evacuate, then everybody can run away easily in 3 seconds. There's a small resistance. Okay. So it's the same what you've done in electricity, in EBN, and heat transfer is very similar. This resistance has a huge influence. And it is not about engineering judgment and understanding what you're doing. It's not about go and calculate this and that and just add it together and then do the calculation. It is about you applying your mind and understanding what the effect is of these resistances, which one is the biggest one and will have the most influence, and which one is negligible. Let's look at this case, for example. The conduction resistance is about 0, and the convection resistance is a value. So let's suppose this is 0.001, and that resistance is 100. And you as an engineer want to increase the heat transfer rate. Well, one option is to say, all right, I'm using copper here. Now I want to use gold or something like that, or carbon with conductivity much, much higher, but it is going to cost me 1,000,000 times more. While in this case, the material that is being used is wood, and I would just like to change it to copper, and it's going to be a few bucks. So the solution will not be trying to change that conduction resistance. The solution would be you need to change the place where the biggest resistance is. The same here. That is the resistance through the door. And that would be the resistance of, if all of you must evacuate through that one door, that is going to determine the resistance. It's going to determine how many people can go through that door in 3 seconds. If you want everybody to be able to leave here in 2 seconds, you need to knock down all the walls. So you should know where you should concentrate on. So that would be in this case. In that case, you will see, for example, I have to concentrate on the resistance of the body if I want to increase the heat transfer rate. And in this case, it would make sense to give resistance to give attention to both the terms, because both of them have a significant influence on the heat transfer rate. Ladies and gentlemen, this analogy that I've showed here is very, very important on the work that we're going to do in the next chapter, because that is going to bring us to the Biot number, which is going to determine and tell you which cases this fancy derivation that has been derived, that is going to lead you to determine in which cases you may use that derivation. Thank you very much, and I'll see you again on Thursday.